The universe we see is only a thin veil of what exists. The release of stars, the dance of galaxies, everything visible is actually the smallest part of the cosmos. But what unknown and little-known truths are hidden behind the veil? Are you ready to discover the deepest secrets of the universe? Because what we see is only 5% of the universe. The remaining 95% is dark, visible, and largely ununderstood. If you enjoyed this video, please don't forget to like it and subscribe to our channel. That way you won't miss our future content. The visible universe presents itself as a luminous tapestry of stars, nebulae, and galaxies, but this glowing structure is not the main story. Most of what exists does not shine, does not collide in the familiar way, and does not respond to light at all. The ordinary matter that composes stars, planets, and living beings is only a thin layer on top of a far deeper and stranger foundation. The universe is dominated by components that are not part of everyday experience, and their quiet rule shapes everything that can be seen. Dark matter reveals itself indirectly, like a hidden hand tugging on the motions of galaxies and clusters. Spiral galaxies rotate too quickly at their edges for their visible matter alone to hold them together. Their outer stars orbit as if embedded in a massive, invisible halo, a structure that outweighs the luminous disk by a large factor. Gravitational lensing confirms this unseen mass, bending and distorting the light of distant galaxies in ways that luminous matter alone cannot explain. The invisible halo imprints its presence on the curvature of space-time, revealing a shadow map of mass where no light originates. In galaxy clusters, hot gas glows in X-rays and galaxies whirl within a shared gravitational well. Yet, detailed measurements of the cluster dynamics show a persistent discrepancy. There is far more gravity than all visible constituents can supply. When clusters collide, as in the famous bullet cluster, the normal matter in the form of gas interacts, collides, and slows, but the main gravitational mass does not linger. Instead, it passes through almost unaffected, like a ghostly component sliding through the turmoil. Maps of gravitational lensing and maps of hot gas diverge, drawing a picture in which most of the mass refuses to collide, radiate, or slow down in familiar ways. This silence is not merely a lack of light, it is a refusal to participate in the interactions that define ordinary matter. Dark matter seems to ignore electromagnetism almost completely, rarely if ever scattering photons or charged particles. It may interact only gravitationally, or perhaps through a new, extremely weak force beyond the known set. Detectors deep underground or under mountains patiently watch for rare collisions between hypothetical dark matter particles and atomic nuclei, but years pass quietly, with only hints and controversial signals. The absence of clear detection is not proof of non-existence, it simply underscores the subtlety of whatever is out there. Some of the lesser-known hypotheses about dark matter paint even stranger pictures. It might be made of ultralight particles whose wavelength is comparable to the size of galaxies, forming vast, coherent quantum states that wash through halos like a single, collective wave. In such models, the innermost regions of galaxies would be smoothed out, avoiding sharp density peaks that would otherwise form. Alternatively, dark matter might clump into small, dense substructures, mini-halos that once hosted the earliest stars, or primordial black holes that emerged directly from fluctuations in the infant universe. These possibilities inhabit the borderland between cosmology and particle physics, where almost everything is constrained only by hints and shadows. Even more elusive is the entity known as dark energy, a smooth, pervasive component that drives the accelerated expansion of the universe. When distant supernovae were used as standard candles to map cosmic expansion, their light arrived dimmer than expected in a decelerating universe. The data pointed toward a startling conclusion. Expansion was not slowing under gravity's pull, it was speeding up, as if pushed by a vast, uniform repulsive influence woven into the fabric of space-time itself. This acceleration is not the rapid stretching of space seen in the earliest inflationary epoch, but a gentler, persistent pressure, subtle yet inexorable. Its density does not dilute as the universe expands, it stays roughly constant, so that as galaxies move farther apart and matter thins out, dark energy's relative dominance grows. It does nothing locally, barely influencing the scales of galaxies or clusters, yet on cosmic scales it dictates the fate of everything. One of the lesser-known puzzles of dark energy is the cosmic coincidence problem. At the present epoch, the density of dark energy and the density of matter, both dark and luminous, are of the same order of magnitude. In the early universe, matter density was far higher and dark energy, if constant, was negligible. Far into the future, matter will be so diluted that dark energy will utterly dominate. Yet observers arise at a time when both are comparable. This delicate balance is fleeting, a brief moment in cosmic history when matter and dark energy share influence. The question of why conscious observers find themselves precisely in such an era is one of the quieter but deeper riddles of cosmology. Another lesser-known fact is that dark energy might not be constant at all. It could be a slowly rolling field, its energy density changing extremely gradually over cosmic time. In such scenarios, the current period of acceleration would be one phase among many, potentially transitioning into different regimes where acceleration halts or reverses. Observations of distant galaxies and subtle imprints in the cosmic microwave background are being pushed to their limits to test whether the universe's acceleration is truly driven by a cosmological constant or by something more dynamic. In some speculative perspectives, dark energy might be a sign that our understanding of gravity itself is incomplete. Rather than adding a new ingredient to the cosmic inventory, these ideas suggest modifying the rules of how space-time goes in response to matter and energy. On large scales, gravity might weaken or behave differently, producing an accelerated expansion without invoking a mysterious fluid. These modified gravity theories must thread a narrow path, matching all known tests of general relativity in the solar system and in binary systems while diverging only in the cosmic realm. The precision of modern observations continually tightens the constraints, pruning away many versions but leaving open the possibility that gravity harbors long-range subtleties not yet grasped. Taken together, dark matter and dark energy form a silent majority composing roughly 95% of the universe's total energy content. The familiar world of atoms, radiation, and visible structures is relegated to a small minority. The deeper, less widely discussed fact is not just that most of the universe is invisible, but that its dominant contents do not resemble ordinary matter in their behavior, interactions, or role in cosmic evolution. The universe, in its most fundamental makeup, is not built from the same materials that compose the everyday environment. It is a vast architecture of unknowns, with luminous matter tracing only the finest outlines of a hidden structure. The scenario of the cosmos is, therefore, profoundly lopsided. What can be directly studied is a surface phenomenon, a scattered population of glowing islands adrift in an ocean of something else. The little-known truth is that the story told by stars and galaxies is incomplete by design. They are not the main characters but supporting actors in a drama governed by dark components that have yet to yield their true identity. As the universe expands and ages, these silent influences will only grow more dominant, while the luminous structures that first drew attention will thin and fade, leaving the hidden majority to dictate the universe's distant future. The universe is filled with a faint afterglow from its hot beginning, the cosmic microwave background, but this familiar relic is only one layer in a much richer and more subtle set of cosmic backgrounds. Space is suffused with seas of nearly undetectable particles and waves, remnants of different eras and processes, each carrying information about conditions that can never be recreated in laboratories. These backgrounds form an invisible ocean, one that permeates every region yet is almost never felt directly. One such hidden sea is the cosmic neutrino background. Neutrinos, nearly massless particles that rarely interact with matter, were once in thermal equilibrium with the primordial plasma of the early universe. When the universe was less than a second old and intensely hot, neutrinos scattered frequently, sharing energy with other particles. As expansion continued and the universe cooled, the density dropped and neutrinos decoupled, streaming freely through space ever since. Today, this background of relic neutrinos fills the cosmos with an enormous number density, outnumbering the photons of the cosmic microwave background by a factor of order 1. These relic neutrinos are incredibly cold and slow by now, their energy is so low that they are nearly impossible to detect directly. Yet their presence subtly influences the growth of cosmic structures and leaves faint signatures in the pattern of temperature anisotropies in the microwave background. Their tiny masses, each species carrying a whisper of rest energy, affect how matter clumps on large scales. This influence allows cosmologists to infer upper limits on the sum of neutrino masses, using galaxies and background radiation as a kind of cosmological balance. The universe thus becomes an instrument for weighing ghostly particles that pass through matter almost unhindered. Beyond neutrinos, the universe hosts a diffuse background of gravitational waves, ripples in spacetime generated by countless processes. Some waves arise from relatively recent events such as mergers of black holes and neutron stars, while others could be primordial, generated during the earliest fractions of a second after the Big Bang. These primordial gravitational waves, if they exist at detectable levels, would encode information about inflation or alternative early universe scenarios, carrying imprints of energies far beyond the reach of particle accelerators. The cosmic gravitational wave background is not like light that can be blocked or scattered. It passes through matter with no impunity. Galaxies, clusters, and even entire walls of cosmic structure are almost transparent to these ripples. Their detection requires exquisitely sensitive instruments capable of measuring changes in distance that are far smaller than the size of a proton, or arrays of pulsars timed with extraordinary precision over many years. The presence of such a background, if confirmed in detail, would become a new kind of map revealing the universe's history in vibrations rather than in photons. There is also the cosmic infrared background, a diffuse glow arising from dust-enshrouded star formation across cosmic history. Many stars are born in dusty nurseries where their light is absorbed and re-emitted at longer wavelengths. Integrated over billions of years in uncountable galaxies, this reprocessed starlight forms a background field that, while faint, carries a record of how vigorously the universe formed stars at different epochs. The detailed structure of this background, its small-scale fluctuations and spectral features, encodes information about the rise and fall of star-forming galaxies, including systems too faint or too distant to be observed individually. Moreover, high-energy processes contribute to a cosmic X-ray and gamma-ray background. Accretion onto supermassive black holes at the centers of galaxies, jets launched by active galactic nuclei, and cosmic ray interactions all produce radiation that, when summed over the sky, becomes a nearly uniform glow. Some portion of these backgrounds has been resolved into individual sources, but a significant fraction remains unresolved, representing populations of faint or distant objects and possibly new classes of phenomena. The unresolved component is a frontier where new physics or astrophysical processes might be hiding. Another subtle background is formed by ultra-low frequency radio waves, whose wavelengths can be comparable to planetary or even larger scales. The ionized gas of the Milky Way and the intergalactic medium can absorb or scatter these waves, making them difficult to detect directly from the ground. Yet these long wavelength fields are expected as a natural consequence of cosmic processes. Future instruments, perhaps located on the far side of the moon to shield them from terrestrial interference, may one day map this background, revealing aspects of the cosmic environment that are currently hidden behind a veil of plasma effects and human-made noise. All these backgrounds coexist, filling each point in space with layers of radiation and particles. The Earth, the solar system, and every galaxy are immersed in them constantly. The little-known truth is that the empty space between galaxies is anything but empty. It is filled with a faint but intricate superposition of relics from different cosmic epochs. Each background corresponds to a different chapter in the universe's history, preserved not in stones or fossils but in subtle fields and particle populations that require ingenious techniques to decode. Another rarely emphasized fact is that backgrounds do not merely tell stories about the past, they actively shape the present and future evolution of the cosmos. Relic neutrinos and photons contribute to the overall energy density, influencing the rate of expansion and the growth of structure. Gravitational wave backgrounds can, in principle, affect the dynamics of extremely large-scale configurations. High-energy backgrounds regulate the ionization state of the intergalactic medium and participate in feedback processes that govern galaxy evolution. The universe, then, is not just a scene lit by a single afterglow. It is a layered palimpsest of invisible seas, each representing a silent choir of particles and waves left over from processes long concluded. These backgrounds are not fully mapped and not fully understood. As instruments become more sensitive, they slowly transform cosmic emptiness into a rich archive of subtle signals, each carrying a fragment of the universe's story that has never been told in full. On the largest scales, the universe does not resemble a uniform sea of matter, nor a random scattering of galaxies. Instead, it organizes itself into a pattern reminiscent of a three-dimensional web. Galaxies cluster into groups, groups into clusters, and clusters into superclusters, all linked by elongated filaments. Between these structures lie vast void regions where matter is sparse and galaxies are few. The true shape of the cosmos is that of a cosmic web, and the lesser-known aspects of this structure reveal how gravity sculpts the universe in ways that defy naive expectations. In the early universe, matter was distributed almost uniformly, with small fluctuations in density. Over billions of years, gravity amplified these tiny variations. Regions slightly denser than average attracted more matter, while slightly underdense regions lost material to the surroundings. As a result, matter flowed out of voids and into filaments and nodes, amplifying the contrast. This process naturally produces a web-like pattern without the need for any favored directions or pre-existing scaffolds. Gravity alone is sufficient to weave the structure. Filaments are not mere chains of galaxies. They are extended, thread-like concentrations of dark matter and gas, sometimes spanning hundreds of millions of light years. Galaxies form within these filaments, often aligned along their axes. Gas streams along the filaments toward the densest nodes, feeding galaxy clusters like rivers delivering material to a basin. These inflows help sustain star formation in cluster galaxies and regulate the supply of fresh matter for future generations of stars. Voids, by contrast, are often imagined as empty gaps, but their properties are more nuanced. Voids are underdense regions, yet they are not complete vacuums. They contain dark matter, diffuse gas, and isolated galaxies that have evolved in relative isolation. The conditions within voids differ profoundly from those in crowded clusters. Lower interaction rates between galaxies, weaker tidal forces, and a quiet environment can lead to evolutionary paths that diverge from those in denser regions. Some void galaxies are surprisingly gas-rich and form stars at steady and disturbed rates, offering a window into a less perturbed mode of galactic evolution. One lesser-known fact is that voids contribute to cosmology not only as empty spaces but as powerful tools for measuring the universe's properties. The shapes and sizes of voids, and how they are distributed, are sensitive to the underlying cosmological parameters, including the nature of dark energy and the sum of neutrino masses. As spacetime expands and structures grow, voids become larger and emptier. Their statistics, when properly analyzed, complement galaxy clusters and supernovae as probes of cosmic acceleration and the growth of structure. Another subtlety lies in the way light and matter move through the web. Photons traveling from distant galaxies to observers thread their way through a landscape of gravitational potentials created by filaments and voids. As they pass through overdense regions, their paths bend and their energy shifts slightly. Similarly, as they traverse underdense regions, the change in gravitational environment can leave a faint imprint on their frequencies and directions. These integrated effects show up as delicate signatures in the cosmic microwave background and in the apparent distribution of galaxies across the sky, providing indirect evidence of the web's detailed structure. The cosmic web is not static. Filaments can reconfigure, merge, or stretch. Voids can expand and occasionally fragment. Over immensely long timescales, as dark energy drives accelerated expansion, the web will thin. Matter-locked in gravitationally bound structures will remain cohesive, but the filaments linking them will become more tenuous. Eventually, distant nodes will drift beyond observational reach. The architecture of the web will persist locally but lose its connections on scales that once united vast regions into a coherent structure. Within the web, galaxy clusters act as knots where multiple filaments intersect. These regions are rich in dark matter and hot gas, and they play host to some of the universe's most energetic phenomena, including powerful jets from supermassive black holes and enormous shock fronts. Yet, an often overlooked aspect is that these clusters also register the influence of surrounding voids. The external environment affects how material flows into the cluster, how substructures merge, and how cluster shapes evolve. The web, in other words, is an interconnected system where even apparently isolated knots bear the imprint of the surrounding emptiness. On smaller scales within filaments, there exist finer subfilaments and sheets revealing a fractal-like pattern. Simulations show that matter distribution acquires complexity at many levels, with small-scale structures embedded in larger frameworks. This nested hierarchy challenges any simple description of cosmic structure as either smooth or clumpy. Instead, the universe presents a continuum of structures whose statistical properties change with scale in ways that encode the laws of gravity and the initial conditions of the cosmos. The cosmic web also mediates the thermal history of the universe. Gas falling along filaments can be shock-heated to high temperatures, contributing to the so-called warm-hot intergalactic medium, a tenuous phase that may contain a large fraction of the universe's normal matter. This warm-hot component is difficult to observe directly because of its low density and intermediate temperature. Its detection requires careful analysis of absorption lines in the spectra of distant quasars or subtle emission features. The fact that so much ordinary matter hides in filamentary gas, rather than in stars or cold clouds, is another lesser-known facet of cosmic structure. The web's existence challenges intuitive notions of emptiness and isolation. What seems like vast gaps between galaxies are often parts of coherent patterns shaped by gravitational flows that span hundreds of millions of light years. The universe is not a random sprinkling of islands in a void, but a continuous network where matter, energy, and history are intertwined. The lesser-known reality is that every galaxy, even one apparently alone in a dark region, is embedded in and influenced by this larger framework, connected by threads of mass and history that extend far beyond its visible edges. The laws of physics, at their fundamental level, often appear symmetric with respect to time. Many equations remain valid if time is run backward, suggesting that the universe could, in principle, proceed in reverse without violating those rules. Yet the observed world displays a clear temporal asymmetry. Eggs break but do not spontaneously reassemble, stars burn fuel and do not unburn it, and memories form of the past but not of the future. This discrepancy between time-symmetric laws and time-asymmetric experience is anchored in subtle and lesser-known features of the cosmos. One key perspective lies in the thermodynamic arrow of time, defined by the direction in which entropy increases. Entropy, a measure of disorder or the number of microscopic configurations compatible with a given macroscopic state, tends to grow in isolated systems. The universe, taken as a whole, has evolved from an early state that appears, from a coarse-grained viewpoint, to have been extraordinarily low in entropy. The existence of such a special initial condition is itself a profound and rarely fully appreciated fact. The early universe, hot and nearly uniform, might seem simple and therefore high in entropy, but under gravity, uniform mass distributions can correspond to low entropy compared to clumped configurations dominated by black holes. As gravity drives matter into more complex structures, entropy increases. Galaxies, stars, and black holes form, and irradiation disperses energy in ways that are increasingly difficult to reverse. The thermodynamic arrow of time, in this view, is tied not to the local laws alone, but to the global boundary condition of a low entropy beginning. Without that special initial state, the flow from order to disorder that defines everyday experience would not be so one-directional. The universe's earliest configuration, therefore, does not just precede everything, it selects a direction in which change appears irreversible. Another subtle arrow is the cosmological one, defined by the expansion of the universe. From the hot, dense early state, space has been stretching, increasing distances between galaxies. This expansion provides a global sense in which one can say the universe had a younger, denser past and will have an older, more dilute future. While the underlying equations permit solutions in which the universe contracts or cycles, the observed universe is currently in an expanding phase. The alignment of the thermodynamic arrow with this expansion, the fact that entropy increases as the universe grows, is not accidental. The larger volume of space allows more possible configurations, and gravity drives the formation of structure that further boosts entropy. On the microscopic level, the situation becomes more intricate. Quantum processes can sometimes blur classical ideas about temporal order. Certain decays and interactions display tiny violations of time reversal symmetry when viewed in detail, often linked to deeper symmetries involving charge and parity. These small asymmetries, known from particle physics experiments, hint at a deeper layer where time is not perfectly symmetric even in fundamental interactions. The connection between these microscopic violations and macroscopic temporal arrows remains an area of investigation, but their existence underscores that time's asymmetry is not solely a matter of boundary conditions. In cosmology, there are hypotheses in which the arrow of time could reverse in distant regions or epochs. Some models imagine a universe that, on the largest scale, is time-symmetric, with entropy increasing away from a central low-entropy slice in both temporal directions. Observers on either side would perceive their own arrow pointing away from that middle state, each believing their side to be the forward direction. The lesser-known implication is that what is perceived as the future might be mirrored by another domain where the arrow points in the opposite sense, yet no communication between the two is possible. Another layer of subtlety appears when considering horizons. In an accelerating universe, observers possess cosmological horizons beyond which events can never affect them. These horizons, like black hole horizons, carry an associated entropy and temperature, linking the arrow of time to the properties of space-time boundaries. As the universe continues to accelerate under dark energy's influence, the existence of a horizon with a fixed area implies an upper bound on the observable entropy for any given observer. In such a context, time's arrow is not just a matter of local processes, but is bound up with the global structure of space-time and the ultimate limits on what can be known or influenced. Another hidden asymmetry involves the flow of information. In realistic situations, information about detailed microstates is continually dispersed into inaccessible degrees of freedom. Radiation carries away correlations, interactions scramble them, and the practical ability to reconstruct past states erodes rapidly. While the underlying dynamics might be unitary and information-preserving, the coarse-grained description experience is an effectively one-way loss of usable information. This informational arrow aligns with the thermodynamic one and with the psychological arrow defined by memory and perception. On cosmic scales, time's arrows intersect and sometimes diverge in subtle ways. The acceleration of expansion implies that large portions of the universe will eventually slip beyond mutual causal contact, locking in certain patterns permanently. Structures that would once have interacted become isolated, and entropy locally approaches equilibrium while globally the universe's available phase space continues to expand. The deeper fact, often overshadowed by more familiar images of expansion, is that the universe's temporal asymmetries are woven from a combination of initial conditions, gravitational dynamics, quantum effects, and the existence of horizons that limit what can ever be experienced. The arrow of time, therefore, is not a simple overlay on an otherwise symmetric stage. It is an emergent feature shaped by the universe's boundary conditions and global structure. The lesser-known reality is that understanding time's direction requires looking not only at local experiments or microscopic laws, but at the entire history and geometry of the cosmos. Time's hidden asymmetries are written into the way the universe began, how it expands, how it clumps, and how it limits observation, threads of a pattern that turn temporal flow into one of the universe's most profound and quietly constrained facts. At everyday scale, space-time appears smooth and continuous. Distances can be measured with arbitrary precision, at least in principle, and trajectories can be traced along well-defined paths. Yet theoretical considerations suggest that at the smallest conceivable scales, spacetime may be anything but smooth. Near the Planck length, an unimaginably tiny distance, quantum fluctuations are expected to disrupt any notion of a congeometric background, replacing it with a restless, foamy structure. The Planck scale is set by combining fundamental constants, the speed of light, Newton's gravitational constant, and Planck's constant. It marks a regime where quantum effects of gravity can no longer be ignored. At such scales, spacetime itself is expected to participate in the uncertainty that governs particles and fields. Distances and durations might lose their classical meaning, and the concept of a smooth manifold could break down. While no direct experiments can reach these scales, theoretical arguments and indirect considerations hint at this frontier's character. One way to picture quantum foam is as a sea of fleeting fluctuations, where virtual black holes and wormhole-like distortions briefly appear and vanish. In this view, spacetime at the smallest scales is like a turbulent fluid, with topology and geometry fluctuating rapidly. These fluctuations might be suppressed at larger scales, averaging out to produce the smooth geometry described by general relativity. But at the Planck frontier, no averaging has yet occurred, and the underlying chaos becomes dominant. Various approaches to quantum gravity attempt to formalize this intuition. In some loop-based theories, spacetime geometry is quantized, with area and volume taking on discrete spectra. The continuum emerges only when many such quanta are combined, analogous to how a solid surface appears smooth from afar despite being composed of atoms. In other approaches, strings of more abstract objects replace point particles, smearing interactions over tiny but finite lengths and softening the infinities that plague naive attempts to quantize gravity. In each case, the deep message is that spacetime near the Planck scale is structured in a way that has no direct classical analogue. An often overlooked implication is that the vacuum itself, in such a picture, is far from empty. Quantum fields and curved spacetime are known to exhibit zero-point fluctuations even in their lowest energy states. When gravity is added to the mix, these fluctuations may couple back to geometry, contributing to what is effectively a vacuum energy. The naive expectation is that this energy density should be enormous, many orders of magnitude larger than what is inferred for dark energy. The discrepancy between theoretical estimates and observations is one of physics' greatest unsolved problems, known as the cosmological constant problem. It suggests that the interplay between quantum vacuum and large-scale curvature hides mechanisms that are deeply unfamiliar. Another lesser-known idea is that quantum foam might induce tiny violations of Lorentz invariance or other symmetries at extremely high energies. If spacetime is not perfectly smooth but has a granular structure, then particles traveling at near light speeds over cosmological distances might accumulate minuscule deviations from expected behavior. Observations of high-energy cosmic rays and gamma rays from distant sources can, in principle, test for such effects. So far, constraints are severe, suggesting that any such deviations must be extremely small, but the possibility remains the subtle imprints of the Planck frontier are hidden within astronomical data. In some scenarios, quantum spacetime might act as a sort of medium with refractive properties. Different wavelengths of light or gravitational waves could propagate with slightly different effective speeds due to interactions with the underlying microstructure. Over immense distances, these differences could build up, altering arrival times of photons from distant bursts or modifying the phase of gravitational waves. The absence of observed distortions in many cases places stringent limits on how violent or anisotropic the quantum foam can be, pushing theories toward forms where the small-scale structure is either more uniform or more subtle in its influence. Another angle on the Planck frontier comes from black hole physics. Near the event horizon of a black hole, quantum effects give rise to Hawking radiation, a process in which pairs of particles seemingly appear from the vacuum, with one escaping and the other falling inward. This phenomenon ties together quantum mechanics, thermodynamics, and general relativity, suggesting that spacetime near horizons carries microscopic degrees of freedom that account for black hole entropy. The implication is that geometry is not merely a passive stage but a thermodynamic system with underlying microstates. If spacetime has microstates, then the entire universe can be thought of as a kind of emergent thermodynamic object. Some ideas propose that gravity itself arises from the statistical behavior of unknown microscopic constituents of spacetime, much as elasticity emerges from the collective behavior of atoms in a solid. In this emergent gravity view, the smooth equations of general relativity are akin to equations of state, not fundamental laws. The deeper information resides in patterns that are near the Planck scale, far below direct observational access, yet subtly controlling the large-scale motions of galaxies and the expansion of the universe. The quantum foam, then, is not merely a mathematical curiosity at unattainable scales. It is a pointer toward a layer of reality where space and time are no longer the primary ingredients but emergent properties. The little-known implication is that everyday notions of distance, duration, and geometry might be as approximate and emergent as the familiar concepts of temperature and pressure. Beneath them lies a regime where these quantities dissolve into more primitive entities whose nature remains one of the great unsolved mysteries. Black holes occupy a central place in modern astrophysics, described in textbooks as regions where gravity is so intense that not even light can escape. Their properties event horizon, singularity, mass, spin, and charge are encapsulated in elegant solutions of general relativity. Yet beyond these idealized forms lies a menagerie of more exotic compact objects, some hypothesized and some constrained, that expand the landscape of what gravity might assemble. One such possibility is the primordial black hole, a type of black hole that could have formed not from collapsing stars but from density fluctuations in the infant universe. Shortly after the Big Bang, regions slightly denser than their surroundings might have become gravitationally bound and collapsed directly into black holes of various masses, from microscopic to enormous. Depending on their mass distribution and abundance, such objects could contribute to or even dominate the dark matter. Observational searches for microlensing events, for Hawking radiation from evaporating low-mass black holes, and for gravitational wave signatures from mergers have placed strong constraints on many mass ranges, but windows remain open. Another class of hypothetical objects arises when considering the possibility that what is thought of as a black hole is, in some circumstances, a different structure entirely. Brava stars, for example, are speculative constructs where an ultra-dense shell of matter or exotic energy surrounds a region of spacetime markedly different from both normal vacuum and ordinary matter. Their properties could mimic those of black holes from a distance, but differ near what would otherwise be the event horizon. Distinguishing such objects from true black holes requires exquisitely precise observations of horizon-scale phenomena, such as the shadow images produced by infalling light or the detailed ringdome patterns in gravitational waves after mergers. Boson stars represent another intriguing possibility. Composed of scalar particles, such as hypothetical ultralight bosons, these stars are bound not by ordinary pressure but by a combination of gravity and quantum coherence. In some models, they could grow to substantial masses and occupy galactic centers, playing roles similar to supermassive black holes but without event horizons. Their gravitational fields would be strong, yet their internal structure would differ markedly from that of traditional compact objects. Signatures of such entities might hide in peculiar gravitational wave signals or in deviations from expected motion of stars and galactic cores. Even more exotic are theoretical constructs like naked singularities, where the singularity predicted by general relativity is not hidden behind an event horizon. The cosmic censorship conjecture supposes that such singularities cannot arise in realistic circumstances, protecting the predictability of spacetime by concealing regions where classical physics breaks down. Yet exact solutions exist that contain naked singularities, and it remains an open question whether nature permits them in any form. If they did exist, their observational fingerprints would likely be extreme and chaotic, a regime where known physics might not provide reliable guidance. Wormholes, hypothetical tunnels connecting distant regions of spacetime, are another feature of general relativity that has captured the imagination. While traversable wormholes require exotic matter that violates familiar energy conditions, they are not outright forbidden by the equations. If such structures exist or existed, they could, in principle, allow shortcuts between distant regions or even between different universes in a multiverse framework. The stability, formation, and persistence of wormholes are all fraught with theoretical difficulties, yet they remain as markers that space-time geometry can admit configurations far stranger than simple curves and warps. Compact objects could also conceal more subtle deviations from standard behavior. For instance, near-horizon quantum effects might modify the classical picture in ways that alter how matter falls in or how information escapes. Proposed structures such as fuzzballs in string theory replace the classical notion of a singularity with a tangled, extended configuration of strings and branes, each black hole becoming a specific quantum state rather than a featureless geometry. These ideas aim to reconcile black hole thermodynamics and information conservation, suggesting that what appears as a simple object from afar may harbor an astronomical number of internal degrees of freedom. Observationally, gravitational wave astronomy has opened a new window on compact objects. The detailed waveforms emitted when two massive bodies spiral together and merge contain information about the nature beyond simple mass and spin. Deviations from expected templates could hint at non-standard structures or additional fields. The ring-down phase, during which the merged object settles into equilibrium, is especially sensitive to the properties of the final configuration. Precision studies of this phase could reveal whether the object truly behaves like a classical black hole or whether subtle echoes or modulations point to more exotic possibilities. The lesser-known reality is that the universe's inventory of compact objects might be more varied than the canonical categories suggest. While neutron stars and black holes provide the clearest examples confirmed by observation, theoretical landscapes include a broad spectrum of alternative configurations. Many may never exist in nature, forbidden by formation pathways or instabilities. Yet their theoretical existence demonstrates that gravity's capacity to assemble matter and energy into bound states is not limited to the familiar. The true diversity of compact objects, whether realized or merely potential, becomes a quiet testament to the richness of solutions that spacetime permits. One of the most surprising threads in modern theoretical physics is the idea that the amount of information that can be contained within a region of space is not proportional to its volume but to the area of its boundary. This insight arises most clearly in the study of black hole thermodynamics, where entropy, the measure of information content, scales with the area of the event horizon rather than with the volume enclosed. This area law is not only a curiosity, it is a hint that the fundamental description of the universe might be holographic in nature. In a holographic picture, a higher dimensional region can be fully described by degrees of freedom that lie on a lower dimensional boundary. The bulk physics is encoded in surface data much as a holographic plate encodes a three-dimensional image on a two-dimensional surface. This is not merely an analogy. In certain spacetimes, precise mathematical dualities have been formulated that relate a gravitational theory in a higher dimensional bulk to a quantum field theory on its lower dimensional boundary. These correspondences suggest that what is perceived as a volume filled with fields and particles could, in some sense, be a projection of a more fundamental boundary theory. The little-known depth of this idea is that it provides a possible resolution to puzzles about information loss. When matter falls into a black hole, classical reason suggests that its detailed information is lost to the outside world, preserved only in aggregate quantities like mass, charge, and angular momentum. Yet quantum mechanics forbids the destruction of information in isolated systems. The holographic approach proposes that the information about everything that has fallen in is stored in subtle degrees of freedom on or near the horizon, and that the radiation emitted by the black hole is, in principle, correlated in a way that preserves information. Extending beyond black holes, horizon thermodynamics applies also to cosmological horizons and de Sitter-like spacetimes, such as those with positive cosmological constants. observers in an accelerating universe possess horizons beyond which events are forever inaccessible. These horizons too can be assigned an entropy and a temperature, implying that the observable region for any such observer has a limited information capacity. The full universe might contain more, but no single observer can access or encode arbitrarily large amounts of information. From this standpoint, space-time geometry and gravity may not be fundamental, but emergent, arising from the entanglement structure of underlying quantum degrees of freedom. Changes in entanglement across regions can manifest as curvature, and the dynamics of space-time may be recast as thermodynamic relations between information-theoretic quantities. This perspective recasts the Einstein field equations as relations akin to equations of state, compressing the description of geometry into statements about entropy, temperature, and energy flow. The holographic principle also limits how densely information can be stored without collapsing into a black hole. Attempting to pack too many bits into a small region forces the formation of a horizon, effectively capping the information capacity. This bound, expressed in terms of area rather than volume, hints that the true number of degrees of freedom in any region is lower than naive field-theoretic estimates would suggest. The vacuum teems with potential excitations, yet the holographic bound quietly asserts that not all can be independently realized without triggering gravitational collapse. On cosmological scales, if the universe is approximately de sitter in the far future due to dark energy, then its horizon area remains finite, and so does the maximum entropy accessible to any observer. The implication is that there is an ultimate limit to the amount of information that can be stored, processed, or even defined within that observer's causal patch. As time goes on and the observable region effectively shrinks in moving terms, more of the universe recedes beyond reach, and the accessible information content approaches that bound from below. The holographic view therefore transforms the concept of reality from an unbounded three-dimensional arena into something more constrained and layered. What appears as a voluminous world may, at a deeper level, be a projection of a finite information set living on a boundary. The fine details of this encoding remain unknown, but the area scaling of entropy and the robustness of holographic dualities in specific contexts strongly suggest that true bookkeeping of reality is more economical than classical intuition would allow. The quiet implication of these ideas is profound. The universe may not only be governed by geometry and fields, but by principles of information organization that set fundamental limits on what can exist and be known. Gravity, horizons, and entropy become intertwined aspects of a single underlying narrative, one in which the apparent fullness of space is a reflection of patterns inscribed on low-dimensional surfaces. The holographic whisper running through modern theoretical physics thus hints that reality, at its core, may be simpler and more constrained than its rich phenomenology suggests, yet simultaneously deeper in ways that remain only partially glimpsed. The universe's laws and parameters present a collection of numerical values that, when taken together, allow for the existence of complex structures and life. Many of these values could, in principle, have been different, leading to universes that look nothing like the one observed. Among these parameters, certain combinations and balances stand out as especially striking, appearing as cosmic coincidences or instances of fine-tuning. These features do not necessarily imply purpose, but they do raise questions about why reality has settled on this particular set of conditions. One such coincidence lies in the relative strengths of fundamental forces and particle masses. If the electromagnetic interaction was significantly stronger relative to gravity, stars might burn too quickly or behave chaotically, disrupting the long, stable periods required for planetary systems to develop and for life to evolve. If the strong nuclear force was slightly weaker, atomic nuclei heavier than hydrogen might be rare or non-existent, preventing the rich chemistry needed for complex molecules. Conversely, if it was slightly stronger, nearly all hydrogen might be bound into heavier elements, depriving stars of the simple fuel that powers long-lived main sequence phases. Another subtle fine-tuning involves the mass difference between neutrons and protons. This small difference affects the stability of hydrogen and the balance between protons and neutrons in the early universe. If the neutron were only slightly light or heavy relative to the proton, the resulting primordial abundances of elements would be drastically altered. The conditions that lead to a universe rich in both hydrogen and heavy elements suitable for building stars and planets emerge from a narrow window in this mass difference. The cosmological constant associated with dark energy presents an even more extreme fine-tuning challenge. The observed value is incredibly small compared to naive theoretical expectations, yet not exactly zero. If it were much larger and positive, the universe's expansion would accelerate so rapidly that matter would fly apart before galaxies could form. If it were significantly negative, gravity would eventually overwhelm expansion, causing a rapid collapse. The observed value sits in a delicate range where large-scale structures can form and persist for billions of years, providing habitats where complexity can arise. The timing of cosmic events also features coincidences. The fact that humans find themselves in a cosmological era when dark energy and matter densities are of comparable magnitude is remarkable. In the early universe, matter dominated. In the far future, dark energy will dominate nearly completely. Yet the current epoch is one in which both contributions have similar importance. For observers to exist during such a transient overlap appears improbable in a naive temporal sense, raising questions about selection effects and what conditions are necessary for the emergence of observers at all. The existence of long-lived, stable stars is itself contingent on multiple parameters falling within specific ranges. Stellar structure depends on the balance between gravitational collapse and various forms of pressure, including thermal and radiation pressure. If fundamental constants were slightly different, stars might either never ignite fusion, collapsing into inert objects, or burn explosively with lifetimes too short for planetary systems to stabilize. The interplay of nuclear reaction rates, opacity, and energy transport sets the stage for a stellar population that includes a significant fraction of stars with lifetimes measured in billions of years. From one perspective, these coincidences invite multiverse explanations. If reality includes an enormous ensemble of regions or universes, each with different values of physical parameters, then observers would naturally find themselves only in those domains where conditions permit complexity in life. In this entropic reasoning, fine-tuning is not unexpected, it is a selection effect. Regions where parameters fall outside the narrow life-permitting window may vastly outnumber life-friendly regions, but they remain unobserved because they lack observers. Another perspective explores deeper principles or symmetries that might fix or correlate parameters in ways not yet understood. Perhaps what appears as contingent is in fact determined by consistency conditions of some more fundamental theory, such as string theory or another unifying framework. In this view, the fine-tuning is only apparent, skewed by incomplete knowledge of the constrained landscape. The true space of possible physical laws might be much smaller than currently imagined, tightly restricted by internal coherence, anomaly cancellation, or the mathematical conditions. Less widely appreciated is that some fine-tuning arguments rely on assumptions about what variations are allowed. Changing one parameter while holding all others fixed may not represent a physically realistic deformation of the underlying theory. In a more complete framework, parameters might vary together in correlated ways that preserve certain relationships. Exploring this correlated parameter space reveals that in some directions, habitability might be more robust than first appears, while in others it becomes even more fragile. Regardless of interpretation, the existence of these coincidences is a factual feature of the observed universe. They underscore that the transition from a simple, hot plasma to a structured cosmos with stars, planets, and chemistry is not guaranteed by broad, generic conditions. Instead, it relies on a network of relationships among constants and processes that must fall within specific bounds. The quiet, lesser-known implication is that the universe's apparent naturalness is laid atop a background of delicately balanced quantities, whose deeper explanation remains one of cosmology's most persistent open questions. The standard cosmological model traces the universe's history back to a hot, dense early state often called the Big Bang. Yet this description leaves open what, if anything, preceded that phase and whether the universe's history includes cycles, bounces, or transitions beyond the reach of direct observation. Various models propose that the cosmos may have undergone multiple epochs of expansion and contraction, or that the Big Bang itself was a phase change rather than an absolute beginning. In some bouncing cosmologies, the universe contracts from a large, dilute state, reaches a minimum size where quantum gravity effects become significant, and then bounces into an expanding phase. In such scenarios, the Big Bang is not the origin of time, but a transition point between two phases. The conditions just before the bounce can imprint subtle signatures on the distribution of matter and radiation after the bounce, such as specific patterns in primordial perturbations. These imprints are difficult to distinguish from those of standard inflationary models, but detailed measurements of the cosmic microwave background and large-scale structure may, in principle, reveal differences. Ekpyrotic models conceive of the Big Bang as the result of a collision or interaction between higher dimensional branes in a larger space. The universe's hot, dense beginning arises from this interaction, while the pre-collision phase may have been cold, empty, or slowly contracting. Such models can generate nearly scale-invariant perturbations without standard inflation, though they require intricate mechanisms to produce the observed spectrum. The idea that the visible universe's entire hot phase emerged from a higher dimensional event highlights how limited the usual extrapolation of four-dimensional spacetime may be. Conformal cyclic cosmology offers another vision in which the distant future of one cosmic eon becomes, after an appropriate conformal rescaling, the Big Bang of the next. In this picture, the universe undergoes an infinite sequence of eons, each beginning in a hot, dense state and ending in a cold, dilute, exponentially expanding state dominated by massless or effectively massless particles. The transition between eons occurs when all characteristic mass scales fade away, leaving a geometry that, after rescaling, matches the conditions of a new Big Bang. In such a framework, subtle correlations in the cosmic microwave background might betray signatures of previous eons encoded as patterns that do not fit within a single inflation narrative. Another class of ideas posits that inflation itself might be eternal in some regions, with new pocket universes continually budding off from an inflating background. In such a multiverse, each pocket undergoes its own thermal history, beginning with a localized hot phase that functions as its Big Bang. From the perspective of any one pocket, the Big Bang appears as an origin, but globally, there is no single beginning. Instead, inflation stretches space indefinitely, spawning an intricate, ever-growing mosaic of regions with varying properties. The observable universe becomes one finite patch amidst a far larger and more varied cosmic ensemble. Less well known is that some cosmological solutions allow for universes that are geodesically complete, meaning that past-directed paths can extend indefinitely without encountering singularities. These solutions often require violating certain energy conditions or invoking exotic matter fields, but they demonstrate that the presence of a Big Bang-like hot, dense phase does not necessarily entail a true beginning. The universe's history could be extended arbitrarily far into the past in some models, though such extensions may involve qualitatively different phases or exotic states of matter. Hidden histories may leave only the faintest traces in observable data. Primordial gravitational waves, non-Gaussianities in the distribution of density fluctuations, or unusual correlations at large angular scales in the cosmic microwave background could all be potential signposts. Yet distinguishing these from statistical fluctuations or from signatures of simpler models is challenging. The data that reach observers today are processed by billions of years of cosmic evolution, reducing clear imprints of any pre-Big Bang phase to delicate and contentious hints. The possibility of cosmic cycles or prehistories also intersects with deep questions about entropy. If the universe undergoes repeated cycles, how does entropy avoid monotonically accumulating to a featureless maximum? Some models propose mechanisms for entropy dilution or resetting, perhaps via phases where degrees of freedom become effectively frozen or inaccessible. Others invoke new physics at high energies or in extreme geometries to rewrite thermodynamic expectations. The challenge of reconciling cycles with the arrow of time underscores the intimate connection between cosmology and fundamental statistical principles. The lesser-known reality is not merely that alternative cosmological histories exist as mathematical constructs, but that current observations do not decisively rule out many of them. While the simplest Big Bang plus inflation framework fits data well, room remains for additional layers of history, for pre-inflationary phases, or for a global structure in which the observed hot epoch is one episode among many. The universe may carry within its large-scale structures and background radiations faint echoes of events that precede or transcend the standard narrative, awaiting more sensitive instruments and more refined theoretical tools to decode. The universe's observable history spans billions of years, from the first light after recombination to the present era of galaxies and complex structures. Yet this slice is only part of the full temporal panorama. Projecting forward, cosmology sketches a far future in which the familiar landmarks of stars and galaxies gradually fade, leaving behind a cosmos that bears little resemblance to the current one. In this distant future, the limits of what can be observed in known tighten, and ignorance itself becomes a fundamental feature of reality. In the nearer future, on timescales of trillions of years, star formation will decline as gas reservoirs are exhausted or locked up in long-lived, low-mass stars. Massive stars will have long since burned out, leaving behind white dwarfs, neutron stars, and black holes. Planetary systems will experience dynamical rearrangements as gravitational encounters nudge or eject planets. Some planets may fall into their parent remnants, Others may drift into interstellar space, becoming rogue worlds wandering through the dark. Over even longer timescales, white dwarfs will cool, their residual heat radiated away until they become cold, dark objects. Neutron stars will also radiate away their stored thermal and magnetic energy. Black holes will dominate the population of massive compact objects, anchoring whatever matter remains gravitationally bound. Galaxies will have merged and remerged, and gravitational interactions will gradually eject many stars and remnants into intergalactic space, leaving behind gravitationally bound islands increasingly isolated by cosmic expansion. On stupendously long timescales, black holes themselves will begin to evaporate via Hawking radiation. The smallest black holes will disappear first, with more massive ones taking vastly longer. Supermassive black holes at galactic centers will endure the longest, radiating away the mass over periods so long that standard time units lose intuitive meaning. Eventually, even these giants will vanish in bursts of low-temperature radiation, leaving behind a universe populated primarily by extremely low-energy photons, neutrinos, and perhaps other light-stable particles. The deep future of a universe dominated by a cosmological constant resembles a de Sitter spacetime characterized by an event horizon for any given observer. As time goes on, more and more of the universe's present-day contents will slip beyond each observer's horizon, their light redshifted into undetectable wavelengths. The observable region will become effectively static, limited to the remnants gravitationally bound to the observer's local group, while everything else accelerates away. For inhabitants in that far future, reconstructing the true nature of the cosmos, its origins, its large-scale structure, its expansion history may become impossible. An observer living at such a late epoch, surrounded only by the faint glow of decaying structures within a gravitationally bound region, would see no trace of the cosmic microwave background, no Hubble expansion on observable scales, and no evidence of other galaxies beyond their immediate environment. To such an observer, the universe might appear static and finite, with no clear indication of its early half-phase or its accelerated expansion. The key cosmological clues available today have eroded beyond recovery. The universe would still possess its full history, but that history would become inaccessible in practice. At still later times, if protons are unstable, they may decay, leaving behind a universe of radiation and perhaps a few stable particles such as electrons bound in exotic configurations or other as yet unknown stable relics. Even if protons are stable, quantum mechanical tunneling processes could destabilize bound structures over extreme durations. Matter as it is currently understood would rarefy into ever more diffuse forms, drifting through an expanding space-time where local interactions become increasingly infrequent. The ultimate limits of knowledge are not set solely by the capacities of minds or instruments, but by the structure of space-time and the dynamics of expansion. Horizons restrict which events can ever be observed, while the redshifting of signals and the cooling of backgrounds gradually erase information from practical reach. Even if the underlying physics is fully deterministic and information is never destroyed in principle, the ability of any finite observer to access, decode, and interpret that information is bounded. The late-time cosmos becomes a place where ignorance is not just contingent, but enforced by the geometry of the universe itself. Another rarely highlighted fact is that even now, well before these distant epochs, there exist regions of the universe that are forever beyond observation. The finite speed of light and the finite age of the universe define a particle horizon, the maximum distance from which light could have reached an observer. Beyond this, there may be countless galaxies, structures, and perhaps entire domains with different physical conditions, but they will never be seen directly. The observable universe is thus a finite sample of a potentially vastly larger reality, and inferences about the whole must be tempered by this permanent observational incompleteness. In addition, quantum uncertainty imposes limits on how precisely initial conditions can be known. Even if cosmological parameters are measured with extraordinary accuracy, the exact details of the initial state of the universe remain smeared by fundamental indeterminacy. This uncertainty propagates forward in time, constraining how precisely the universe's detailed history can ever be reconstructed. The combination of horizons, redshift, diffusion, and quantum limits paints a picture where complete knowledge is not merely difficult but logically unattainable. Thus, the far future of the universe is not only a story of physical transformation, but also one of epistemic narrowing. Over time, observers find themselves in smaller, effective islands of accessible reality with diminishing evidence of the cosmos's grand origins and structure. The little-known and humbling implication is that cosmology, as practiced in the current epoch, enjoys a privileged vantage point. The residual heat of the Big Bang is still visible, galaxies are still within view, and the large-scale expansion is still measurable. In this sense, the present is the unique cosmological window, a transient interval during which the universe's fundamental properties are, at least in principle, accessible to investigation. In the remote future, that window will have closed for most observers, leaving behind a quieter, darker, and more opaque cosmos. The universe will persist, but its story will become harder to read. The limits of knowledge, written into space-time and evolution itself, will stand as one of the universe's most enduring and least alterable facts.